All right. Next talk, please welcome Julien, who's going to tell us about profiling in Python. Thank you.
So, okay. So, sorry. So, today I'm going to talk about production profiling for Python. So, if you don't know me, I'm Julien. I worked at Datadog for almost a year now, and I've been doing free software stuff for like 20 years now. This is a boring statement that says that anything that I say today might change in the future, but I have to say that to you. So, first I'm going to talk about what profiling is and what you need it. Then I'll talk about how we built at Datadog a profiler for production system that we use internally that we're going to provide to our customers in the future. So the first thing to understand is what profiling is and why you need it. If you never use profiling, here's the simple answer that it tries to solve. Some of the questions to solve. It's like, if I were to ask you in your program which function or which line of code is going to be the most costly, the most time you're going to spend in your program running and doing that function or that line of code, it will be probably pretty hard for you to guess or to give me an answer, an accurate answer. It's really hard to know when you run programs in production which endpoint is going to spend a lot of time on the CPU, the one line that is going to allocate the most memory in your programs. You might guess, but the more complex your application is going to be, the more complicated it's going to be to answer that question. So the goal of profiling is to actually get inside your program and get all of this data and extract it and be able to say, okay, this is a stack trace that I see the most often. This is a stack trace. So when I talk about stack trace, it's like all of your functions that are being called one after the other. And being able to say, okay, this is what my program is doing, and this is where I need to optimize it to make it faster. Because this is the end goal is to be able to see what your program is doing and to make better decisions about where to spend your time to optimize it. This is typically the kind of output that you will see if you do profiling on a Python program or any kind of program for that matter, where you see stack traces and when the width of the rectangle is like the time spent on CPU or allocating memory or anything like that. There are two types of profiling. The first one is deterministic profiling. So if you ever use cprofile, the Python profiler, which is built in since like a long time in Python, this is what it does. And there's another type of profiling, which is what we're going to talk about today, is like the statistical profiling, where you do things in a different way, which has its own perks. So deterministic profiling, if you never use cprofile or if you don't know it works, it's pretty easy. It actually hooks itself inside Python. It says to CPython, each time you're going to call and execute a function, I want you to tell me, and I will like note down the time it is, and when you finish to execute the function, you just call me again, and I will note down the time, and then I will compute the difference between the two times, and I will know that this function has run for that many seconds. So that's pretty cool. It's pretty easy to understand, but it has a few issues, which is like you only know the hold times. That means you know how much seconds your function has taken, but you don't know what it did. Like, was it waiting for I/O? Was it doing CPU stuff? Was it allocating memory? You have no clue. You just know that it spent 2 seconds executing the function. The way it works is that it hooks itself on functions, which is the granularity that you will get from the output. So if your program is just one giant function, you will have nothing interesting in terms of information. And if your program is thousands of functions or very small functions calling each other, it's going to have so much overhead that your program is going to be 10 times or 20 times slower when it runs. So it's pretty hard to use cprofile in production system for that reason, because the most functions you have in your program, the slower it's going to be. cprofile in particular has this one problem where, in our case, it was an issue where it exports its data also in a custom file format, which is something like pickle, if I remember correctly, which is not something that is really easy to use in any other programming language. So for all of that those reasons, it's impossible to use something like deterministic profiling and C profile in production system. You can't afford to have your web server to run 20 times slower just because you're doing profiling. The other way of doing profiling is different. It's like you're going to run your program normally, you're not going to change anything, but every now and then, like every 10 milliseconds or so, you're going to interrupt your program and to look at what it's doing right now. So what it's going to tell you, if you do that often enough, you're going to have statistically a good representation of what your program is doing usually. So it's not like the absolute truth, contrary to something like C profile, which really meters every call. You're just going to, in that case, statistically over a few hours or a few days of your program running, going to have a number of samples that's going to show you which number of times you see each stack trace. And you're going to have the kind of output that I showed you earlier, which is roughly statistically accurate. The upside of doing that is that you can actually measure a lot of different things, like the world time, but also the CPU time, which tells you if you spend time just doing I/O or actually using the CPU and doing things like computing results. It has a very low overhead. The way it works is that it leaves your program doing what it does usually and does not try to wrap the functions or interrupt them or whatever. It just now and then executes something in the background saying, okay, what is it doing right now? And that's it. You were able, thanks to Python at least, to go down to the line of code that is being executed. So you're not just talking about functions, but you're able to see which line of code in particular is going to be executed. In some languages, not Python, unfortunately, you can go down to the opcode, though the precise operation in the line. That's not possible in Python yet, unless you split your code a lot. And you can have other things like, I'll talk about that later, see the reported the exception running in your program that are being raised, and you're able to see them and to see the control flow in your program. So what I'm going to talk after is what we did at Datadog implementing this. Before doing that, I spent a lot of time checking the state of the art of the dozen of Python profilers out there. None of them does that. A lot of them actually focus on their output, doing fancy flame chart or things like that, which is not something I had to solve. I was only interested into getting the data and exporting them into a proper data format. So what I'm going to talk about just now. So the first thing the first problem I had to solve was how do you get the CPU and world time information? So the way I solved that is in a thread. So you run a parallel thread in your Python program that sleeps most of the time, let's say every 10 milliseconds. You wake up and you're going to use the sys.currentFrame, which is like a private function that has been there forever and that everybody uses, so it's not really private. But what this function returns is a list, a dictionary where the key is a thread and the value is a stack trace, basically. So if you do that every 10 milliseconds, regularly, you're able to each time see which stack is being executed on each thread, and you're able to construct a model where you know, in real time, what your program is doing every 10 milliseconds. When you do that, you can actually use, so that's only Linux specific for this part, function that is pthread get CPU clock ID, which basically returns you a special clock in Linux, which measures the CPU time that each thread is consuming. So every 10 milliseconds, you will be able to get a stack trace and actually associate that stack trace with the number of nanoseconds or milliseconds of CPU that has been used by the thread. So at the end, you get a pretty good representation on each of your threads, what they do, and how much CPU they used. You can actually also get the world time because you can use a regular clock. So you get this kind of output where you have the regular. So this is an example of a Python program with being profiled for 1 minute with 4 threads. That's why you may not see, but there's a 4 minutes on the top root span on the top. There's 4 minutes of world time in total because you got 4 threads running for 1 minute. And you have the detail of which function has been called in which thread. And you have the same data for the CPU time, which is way less. There's only 3 seconds or 5 seconds of CPU time being used. And you see the output looks a bit the same. You see the same stack traces, but you see that a lot of the functions are wait functions that are just doing nothing. So if you were using something like C profile, you would see a lot of time being spent in the wait function, which is not really interesting because it's just a wait function. Where if you take a look at the CPU time, using the data you got from the pthread get CPU clock ID, you actually get the number of nanoseconds being used on the CPU. And you can see here, for example, the wait function We don't see them in the charts below. So as I was saying, it's a way better way to do profiling in production system because it has a very low overhead. So, for example, on my laptop, if I am to profile a Python program with 10 threads, which have each one executing 30 function-long stack traces, I can poll and generate 100 samples per second for only 1% of CPU. So it's already a pretty good thing to get, and it's actually can get a bit cheaper because the way it works, you sleep every like 10 milliseconds, but you can actually increase that amount of sleeping. So if you want to have less impact of your performance, you can dynamically adapt your sleeping time. Like I was saying, you are able to get, so you need to do a bit of C for that, but because it's not exposed in Python, but you actually able to get the profiling exception information. So when you use a block like try except, and it goes back to a few functions before being called, you can see that in Python. It's the equivalent of sys.xinfo. You can catch that and take the control flow of your program. And you can limit the resource usage. I was saying you can basically sleep more often if you need. Right now, the only downside is that we don't do C profiling. So if you have Python module or C module, you're not able to see any information below the Python stack. So that's something I'd like to solve in the next release. We also do memory profiling. So for memory profiling, it's way easier because I would say most of the work has been done already in Python. So there's a Python module since 3.4, which is called Tracemalloc. So what Tracemalloc does is that it replaces the malloc function used by Python to allocate the memory and all the objects that you use in Python by its own wrapper, which allocates the memory, but also make a trace of the allocation. And Tracemalloc is able to export to you the information about which line of code allocated a memory, and like how many megabytes and how many times it has been called. So it's pretty easy to get this kind of information without doing too much work. The problem with Tracemalloc is that it wraps and it counts every object allocation that you do, which makes your program very slow again. So that's not something you can do on production system if you have if you have a program that does a lot of allocation and gets 4 times or 10 times slower just because you are tracing the allocation. It's a problem. So the trick here is to also do sampling and doing statistical aggregation of the results. So the algorithm is pretty simple. Like you sleep most of the time, and once in a while you just wake up and activate or deactivate Tracemalloc to get the samples or not of memory allocation. If you do that like 5% of the time, it's usually okay. You only get 5% of the allocation being tracked by Tracemalloc. But over time, if you do that for a few minutes, a few hours, you get a pretty good representation of your patterns in your application. So it gives you 2 results, as I was saying, the number of allocations that each of your function does and the size. So the 2 charts looks a bit of the same, but I mean the width is going to change based on if the allocation is going to allocate bigger objects or not. But this is the kind of result that you might get at the end with stack traces and the number of megabytes that you're going to have allocated. So pretty easy again to debug your program to see what's costly in terms of memory. So that only count the allocation that you do, not the size of the memory you used. That's only the number of times you allocate memory. It doesn't track like when you free it or if you don't use the object anymore. So right now the limitation of Tracemalloc, like I was saying, is that the overhead it's really slow, really slow. I'm not sure right now how fast you can. I mean, if you can improve it to make it faster. There's no thread information, so the way you track things, it's pretty simple. You don't have any context information about which thread did the allocation, so you can't map that to any threads. And it's also limited in the information entry reports. For the CPU and world time before, it's pretty easy to get the function name because it's reported in the stack. In that case, Tracemalloc just gives you the line number and the file, so you don't know which function or which class you are actually trying to allocate. Even which type of thing you are allocating, it's pretty light in that regard. So that's something I'd love to improve in the future. Another thing where we do a bit of profiling is threading. So usually when you do multi-threading in Python, so a lot of people don't do multi-threading because of the global lock and how it makes things slow, etc. But you still need sometimes to have threads running. When you do application with a lot of threads, you need to synchronize over something, and usually you use a lock, which is like the most basic object you can get in the threading world in Python. And that lock, when you have a lot of threads trying to acquire it, you might have contention, and it might make your program slow. There's nothing in Python to basically to give you that kind of information about, is my thread blocking because it's trying to acquire a lock or not? Is it waiting for too long? Is it waiting forever? What is my contention issue here? Yeah, it's pretty hard to know. So the way we solve that is we basically wrap the threading.lock instances. So each time you create a new lock, you actually get a lock which is not a real lock. I mean, it's a real lock, but under the hood, we intercept it to see when your program is going to acquire it and when it's going to release it. That makes it possible to actually get the information about how much time they spent trying to acquire the lock, or how much time they spent acquiring the lock, like the lock being held by one of the threads. So you get a lot of information. For example, you get the total lock acquire wait time. So this is the number of milliseconds, usually, not that long, that your program is going to wait to acquire that lock. So with this kind of information, you're able to see that you may need more lock, or to split your program in different parts, to not use only one lock, but several locks, etc. You can get all of this information to be able to redesign your program, which is not always easy and possible, but sometimes it is. And you get all of that with the different threads that try to acquire the different locks. So once we built all of that, we had to export all the data to use them, which is its own challenge. So like I was saying, cProfile has its own custom format, not really interesting, not useful for us. There is one format which is pretty used in the world, which is the Valgrind format. So it comes from the Valgrind program, which does profiling for C. And it has its own text-based format that you can use to export data. The problem is that it's text, basically, so it's not really, like, it's easy to consume, but it's not really efficient in any way. And so that's not a good solution for us. Like I was saying, a lot of Python profiler then directly export HTML, so that never gave us any clue on how to export to something that you can use for any other program. Until we found pprof. So if you don't know pprof, it's a lot of things. It's the name of the profiler that is in the Go programming language. It's also the name of the tool they use to display the data, and it's also the name of the format. So it's like the same word for 3 different things. So the pprof format is pretty cool because that's what you can use for, if you do Go and Go profiling, you can export all of your data in pprof format. So it's a format based on protobuf, so it makes it pretty easy to understand. There's a schema with all the fields documented, etc. It's easy to use, and protobuf is easy to use in Python too. It's very fast to serialize, so it would be a shame to try to be fast gathering all the data about your Python program and then being very slow about exporting it. So that's not a problem. The way the pprof format works is not going to export everything that you gather, like every sample with every timestamp, etc. It's going to aggregate all of that. So you're going to compute the sum, the average, the minimum, whatever you need, and export all of that with the stack traces in your format at the end. And it's pretty space efficient, so we use a pretty simple model of a string pool where all your string, because you have a lot of repetition usually, like all the functions you're going to see are always the same. The stack traces are going to be most of the time the same. So all of that is pretty well, I'd say, organized in the schema, and it's gzipped by default. So pretty fast to generate, pretty slow, pretty small to store. For example, on average, we use 20 kilobytes of storage to store 1 minute of profiling for one Python process. So pretty easy to store, even for a few hours or a few days. So pprof is also the name of the tool that you can install pretty easily if you know a bit of Go, but it's not that hard. So it's able to generate this kind of flame chart, which you see on the top left, where you see all the stack traces, and the width is going to be either the size of the allocation that you do in memory, the time you spend on CPU, etc., depending on the statistic that you gathered. Or you can also use this kind of chart on the right, where each rectangle is going to be one function, and everything is going to be connecting by the number of times they call each other, etc. So it's pretty hard to read when you're not used to it, but I promise if you spend like a few minutes on it, and pprof is pretty easy to gather and to understand. So it's easy to use. You can open any pprof file with it, being Go or Python or anything. So what we did at Datalog is an open source library, which is not yet public just because like FOSDEM is too early, but I'm working on it. It's going to be integrated into our tracer library, which is already open source. So the profiling part is going to be integrated into that. And if you want to use it, like you're not using Datalog, it's fine because it also supports exporting the data to a pprof files with an S. So you'll be able to use it directly and to export all the data in pprof and use the tool I showed just before. So as I said, it's not released yet. So if you want to know when it's released, you can follow me on Twitter or anything, and I'll be able to announce it. Should be in a few weeks, no promise, but I hope so. And that's it.
We have 4 minutes for questions. Okay.